Hi, I'm Will Summers, and for Lab 2, describing the motion of falling objects, a lightweight item was dropped on the ground and recorded over time. By using computer models and analyzers, we can make a conclusion for the final position of the object and the different forces as well as the magnitudes that acted upon them. For this specific experiment, we found that the combination of the weight force and the drag force produced the most accurate predictions for our model. For the specific experiment, I used a piece of notebook paper, balled up, and dropped it to the floor from a standing position. Here is my video that I recorded and later used to put onto the computer model for tracker analysis and later to code. Now, as I open the tracker file, you can see that at first I had to tilt the axis a little bit because the camera seemed a bit off angle. Now, as the file plays, you can see as the paper ball drops to the ground, it goes in a parabolic shape as seen by both the graph and the tables presented. In order to compile all the data, I use Newton's second law, force equals mass times acceleration, as well as a variation of the law, final velocity equals initial velocity plus the force net divided by times delta t divided by mass, in order to come up with the values found from the Python model as well as the actual model that we have here. The next step is to input the data into our Python program. Here's a screenshot of the Python with just the weight force acting on it. You can see the mass is at 0.0225 grams, gravity is set at the constant 9.8 meters per second squared, and our time in the while loop is 0.605 seconds. We also use Newton's second law inserted there. However, we just use the weight force in this case, the negative balled weight times the gravity times j hat. We do this in order to see the difference between using just weight force and the drag force. Again, we did this because in the equation we are expecting a non-zero force because of the parabolic motion and the nonlinear velocity as described. Now, as we run the module, these are the two images that are produced. You can see the weight force arrow pointing in the downward direction and our parabolic graph that has been formed due to the force of weight. Okay, here, after compiling all the data into a spreadsheet, and we can see that the graph of the experimental versus model predictions are just slightly off, especially because the model prediction seems to have gone further in position than the experimental position, which is impossible in this case. So we must assume that another force is acting. In this case, it's the drag force. So on our next Python model, we include the drag force. We have the same constants of mass and gravity, as well as time. However, Newton's second law differs in that instead of just applying a weight force, we include the force of drag, which is the magnitude of the velocity squared times a b value. This b value was calculated by inserting different values and running the module several times until the final position of the model was the same as the final position of our experiment. We prove this by running the module, and you can see that not only is the weight force present, but over time the drag force increases as proven by the small arrow above the ball located here. Other than the drag force, the graph of the position over time is relatively the same, only with a few slight changes in the data. Now we can see with the new graph of experimental position versus model position, including drag, that the final position is little to no variance. This is very good, which means that both the objects travel the same distance. Our only discrepancy is here in the middle. However, this could be formed due to other forces, drag, or the camera angle, and things such as. At last, we combined all the data, the experimental position, the model position, as well as the model position with drag, so we can see the difference between the weight force and the weight force including drag. Here, you can see that in the middle position, in the middle of the graph, both model positions seem to be the same. However, as the graph continues, the model position with just weight force differs slightly. In conclusion, by asking the question, what does it mean? You can see that the terminal velocity is not found in either of the predicted models, mostly because the objects seem to be moving too quickly. This can be changed, however, if the drop position was higher up or if the object were to have a lower mass. And finally, for the what if question, if an object were thrown downwards, in this case, then the terminal velocity would remain the same due to the constant mass of the object as well as the proportional forces. However, the velocity would be reached at a faster position. That is all. Thank you very much.